Welcome to Unit 2, Lesson 5. As usual, please look for the tasks to complete list for you. It's tasks for U2L5. You can find it either under assignments or on the Canvas homepage. Since we have a long weekend coming up, I'm going to try to expedite things in class today to help you get through what I would be giving you for homework in class and just make sure you don't have too much work over the long weekend so you can relax and enjoy yourselves. So here's the task list. I checked in with everybody. We'll kind of skip over the little meetings things we normally do. Homework's looking good. I'm seeing 13 posts to the how far you can throw Flipgrid, showing you just throwing, two of your socks. So let me know if you need help on that. Otherwise, the quizzes for the PhET simulation and the Hewitt chapter 5.12 are also looking good. Don't freak out if Canvas gave you a low score on some of those quizzes. I'll go through and manually correct some of the fill in the blank stuff with the numbers because I know there's a little fudging there. The takeaways that I wanted to emphasize is if you fire two projectiles at angles that add up to 90, so for example, if I fired at 30 degrees and at 60 degrees, can anyone tell me what would be true about where those two projectiles would land?
If there was no air drag, they would land in the same spot.
Very good. So they'd land in the same spot, but Quinn, excellent point. This makes actually two big assumptions. The first assumption is that there's no air drag at all, which is not very realistic. Anyone know what the second assumption is? What else has to be true for this to work? Think about the firing level versus the landing level. What has to be true about where it's fired from and where it lands?
Wouldn't those have to be equal?
Yeah, so it has to land at the same elevation that it was fired at. So those are the two assumptions that it makes. So that's kind of an important takeaway there. The only other big question was, why is the statue of David pictured at the base of the cannon? Anyone get it?
I just said size reference, just because it's like I think it's 17 feet tall, so I would assume it's like a size reference.
Anyone been to Florence and seen the David? Yeah, it's almost 2 stories tall. It's very, very big. So yes, that's good thinking, but there is, in my opinion, another reason. Who knows their Bible? Who was David? Or what is David famous for?
He shot down Goliath with his rock.
Very good, right? He battled Goliath with a rock from a sling. And if you've seen the statue of David, he has his arm up to his shoulder, and if you walk around behind it, there's actually kind of like a leather strap going down over his back. It's a sling that he would throw a rock with. That's how he defeated it. So he threw a projectile at Goliath. Get it? Projectile simulator. That's anyway. It took me a long time for that to sink in with me too. So just shows you how nerdy some programmers can be. All right. Any other questions or comments on the homework that was due today? All right, we're going to explore the content from the last section in Hewitt, which was all about orbits. And we'll start off with a short clip from a TV show called Family Guy. Do we have any Family Guy fans here? There's a 40-second clip that we'll watch together here. And I'll just let me optimize the viewing here. All right, check it out.
Peter, I think maybe you're in denial about this fat thing.
Oh, yeah? Well, I challenge you to prove to me that I'm fat.
Okay, hang on. See this?
Yeah?
You know what it is?
Duh, it's an apple.
Good. All right, watch this.
What the hell? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Oh. Oh.
All right. Kind of a silly clip, but and I'm gonna overthink this big time. But Brian's saying that Peter is so fat that things will actually orbit him. So I would like you to answer just a few questions based on this clip and kind of overanalyze it. These are in a Google form that you can find under step number 4. So on the tasks to complete list, step 4, Introduction to Orbit, there's a link to the clip we just watched. And then below that is the Intro to Gravity Family Guy clip Google form. Please click and fill that out. I'll give us about going to time for 10 minutes, but I'm hoping it won't take that long. I'll keep a track on it as people submit it, and once we've got a good amount, we'll discuss it. So 10 minutes to tackle that Google form. Let me know if you need help. So first question was Brian, who's the dog's telling Peter you're so fat that you are pulling objects towards yourself, right? You have your own gravitational force. So most of you understood that that is what he's getting at, right? Your gravitational force is strong enough to pull household objects towards him. Now, again, here's where I might be kind of getting it, overthinking it. Theoretically, why does he throw the apple towards Peter? And the idea is, looks like a lot of you are getting that, you need the force, you need to launch it, right, into orbit, because orbit is really just objects falling around Peter. So if this was actually happening where Peter was exerting his own gravitational force, if Brian held the apple next to him and just let go of it, the apple would fall onto Peter's belly or something, right? Like an apple would fall to earth. But he throws it sideways, and so that gives it enough tangential velocity to fall around Peter continuously. And then he does all those other objects too. Again, overanalyzing it, but that's how orbit actually works, right? Things aren't floating, they're falling around something they're attracted to. So Brian says in short that you're so fat you have your own gravitational pull. Why is this a flawed argument? A little bit of confusion here, but the correct answer is that everything exerts gravitational force, right? So all of you, everyone has their own gravitational pull. If you have mass, you are exerting gravity on the things around you. But we can throw some math in there to show that you're never going to be exerting enough gravity to cause something like an apple to orbit around you. And that's what the final question gets at. And again, I'm seeing you guys actually did much better on this than my other two classes, that's good to see. But the reason why this wouldn't actually work, even if, and I did the math on it a little bit, just trying to throw some numbers in there, but the gravitational constant G that we bring into that equation is a very, very small number, right? It's something times 10 to the negative 11th. And it just shows that gravity is actually a very weak force when it comes to small masses. But when you get to like planetary masses, right, when they're that large, then you can actually see gravity having an effect. Questions or comments on that? So the thing I want to keep emphasizing is this idea of orbit being a falling motion. Things are not floating. It's not like there was zero gravity around Peter. The idea was that he threw the apple next to him and his gravitational force caught it and it started to orbit around him. So I have a video on the task to complete list, which kind of goes over some of the math and elliptical orbit stuff, but I actually just want to go over it with you guys together quickly so that I can let you go to do the next activity, which is the step 5, step 6, which is drawing orbits. So we'll do some math together right now. So I'm just going to highlight my screen here and see how this works. All right, here we go. So we've been talking about orbit. Let's say we've got something like a star, and I've got a planet going around it. And so far, we have talked mostly or visualized it like this. This is my attempt at drawing a circular or circular orbit. What I'm hoping you took away from the most recent reading is this how orbit actually works? Are orbits circular? Give me a yes or no. What do we think? Very good, they aren't. Does anyone know what shape most orbits actually take? Who remembers the term?
An ellipse?
An oval. Oh.
No, this is a very good point. So I heard oval and I heard ellipse, right? And this is something that I used to always think of it too. I used to always think oval. Elliptical or ellipse is the more correct term. And I was trying to look into why, because I also think of that term oval. My understanding is that an oval is kind of like more like an egg shape, right? It's not even. You've got this sort of wide part and another smaller part on the end. That's the idea of an oval. And orbits don't follow. Orbits are definitely a little more symmetric. And so that's why the term ellipse or elliptical is actually the better term to use, because it basically looks like a flattened circle. I'm not very good at drawing these things, but that's what the planet will be following. And usually the star would be over here, closer to one end. So yeah, so don't use that word oval, even though again, I used to do that as well for the longest time. It is elliptical, an ellipse. So there's a weird form of measurement that you can take with ellipses, and that's called eccentricity. And I have this marked on the task to complete list too, but the eccentricity of an ellipse is basically measuring how round an ellipse is, right? How close to a circle is it? And it has to do with 0. So if you have something like 0.2, it's just a ratio of distances that you'll calculate in an ellipse. We have basically focus points, which is what the reading went over. And you're able to do some calculations. You'll have instructions on how to do this. But let's say you have like 0.2 compared to 0.8. A very small number, like 0.2, means it's a very circular ellipse. It's close to a circle. So the closer to 0 you are, the more circular it is, which I like that idea, right? 0, circular. But if it's a higher number, closer to 1, like 0.8, that's more elliptical, like your circle has been flattened to have this more elliptical ellipse shape. So you'll be calculating some eccentricity stuff in the next activity. And again, I have lots of instructions to guide you, so don't worry too much about that. The only other thing to make sure you are familiar with is if I draw a circle with a point at the center, you're also going to be calculating circumference, which is the distance around a circle. And who remembers their geometry? What's the equation for circumference? Anyone remember?
Pi times diameter.
Yes, right. And so it's usually written like this, 2 pi r. But you're right. It's just pi times the diameter. Anyone know what the 2r refers to? What is r referring to?
Radius.
Radius. So 2 times the radius, which is the distance from the center to the thing, which is the same as diameter, and then multiplied by pi. Anyone know the first 3 digits of pi?
3.14.
Oh yeah. You can actually make a lot of money by memorizing that number and reciting the different digits. Anyone know that? You should look into them. They have whole competitions where people just recite pi. Okay, so I'm going to have you do a little exercise now where you, on a blank sheet of paper, are going to draw an ellipse and a circle, and we're going to pretend that these are orbits of planets around a star that's in the center. You're going to use some equipment. Drawing an ellipse is kind of interesting. What you need to do is put a sheet of paper down. You need to put 2 pins into the paper, or you can hold down 2 pencils or whatever you can get. You get a piece of string or floss or yarn, whatever you have, put it over those 2 pins, and then put your pencil in it, and then just stretch it till it's taut and try to draw a circle, and it'll kind of guide you where you'll end up with an ellipse. And in a circle, you can just use your compass, or you can actually probably use the same string that you'll be using. Anyway, I have instructions on the assignment, and I also have a demonstration video that you can watch that I encourage you to actually watch and kind of work along with it. There were 2 push pins in your Science 2 kit, so if you have this sitting around somewhere collecting dust, you can open it up now, and there should be 2 push pins in there that you can use for this activity. And if you have your compass, that might help too. So I will let us go for, let's say, 20 minutes to work on this, and then I will come and check in with you as well. So again, this is step 6 in the tasks to complete, titled Drawing Orbits. So click on that assignment there that says Drawing Elliptical and Circular Orbits, just to show you on my screen what that should look like. When you click on it, here is the assignment it should take you to, Drawing Elliptical and Circular Orbits. Here's what you need. Here's the demonstration video, and here are the instructions on what to do. You'll be submitting a photo to this assignment for that. If you finish with that, you are welcome to move on to the next step, which is the Academia Orbit Simulator classwork. You're going to be using a very simple online orbit simulator to walk through and answer some quiz questions. So again, I'm going to time for 20 minutes to let you work on the drawing thing first, and I'll check in after 20 to see how everybody's doing. And again, if you finish, you're welcome to move on to the next task. Let me know if you have questions. Go for it.